Hello, my name is Ian Collett, and I am a PhD student at the University of Colorado Boulder. I'm a part of the Satellite Navigation and Sensing Laboratory, or SenseLab for short. What follows is a preview of our paper recently published in Navigation. It is titled Characterization and Mitigation of Interference between GNSS Radio Occultation and Reflectometry Signals for Low-Altitude Occultations. GNSS signals are, of course, originally designed for navigation. However, because these signals interact with the environment as they propagate to the receiver, this provides an opportunity to perform remote sensing of Earth's surface and atmosphere. For example, Cygnus satellites collect ocean-reflected signals and estimate ocean surface wind speed. Still, experiments on LEO satellites are limited. The receiver payload must be carefully designed to meet size, weight, and power requirements. What if we used a mountaintop receiver in place of a LEO satellite? With this setup, we can collect high-quality raw data containing multi-frequency, multi-GNSS signals. While not designed for operational use, this type of experiment will help us test new ideas in GNSS remote sensing and signal processing. Our lab has installed an antenna dish near the summit of Haleakala, a volcano on the Hawaiian island of Maui. The dish is positioned so that both the direct line of sight signal and the ocean-reflected signal can be simultaneously collected. Now, let's take a look at a time-lapse of typical dish movement during data collection. The dish will sweep across the horizon, following a low-elevation GNSS satellite. The data collected contains both direct and reflected signals. The paper itself is a case study of one effect we observe in the Hawaii mountaintop data. If the path length difference between the direct and reflected signal is small enough, which can occur for low elevation satellites, the reflected signal will be present as multipath when tracking the direct signal. We determine under what conditions this multipath is present and develop techniques to separate the multipath from the direct signal. Here's an example that illustrates this effect. Focusing on the signal intensity, let's look at minute 21. Notice the higher frequency fluctuations for all three carrier frequencies. This is the reflected signal multipath. At minute 27, these fluctuations have disappeared from L5 in red, but remain on L1 and L2. The chip width of L5 is smaller than L1 and L2, so the multipath effect lasts for a shorter amount of time. Our goal is to wipe the multipath contribution off of the direct signal. The first approach we explore is filtering, which operates on signal intensity in the spectral domain. The second approach we explore is smoothing, which operates on the signal intensity in the time domain. In the full paper, we compare the filtering and smoothing approach and find that the smoothing approach works better, especially at low elevation angles. The performance of the smoothing approach is then quantified through simulation. For more information, please consider reading the full paper. Thanks.